This is Rodney Robertson. I'd like to welcome everybody to our third webinar. This is our agenda for today. We'll ask Stan Graves, who's a member of the Research Advisory Board, to make some introductory remarks. I'll go through some introductory administrative type remarks, and then we'll have our presentation today by Mr. Charles Ellis and Dr. Mike Hamilton, both in microelectronic packaging and nanotechnology, and then Larry Filmer will hold a wrap-up and discussion at the end of the webinar. The webinar will go for approximately 1 hour. So Stan, you'd like to make some introductory comments?
Lonnie, he's not here yet.
Okay,
so
we'll go ahead with the...
I'll let you know.
Okay. We'll go ahead with the administrative comments. The webinar will last for approximately 1 hour. Initially, all webinar participants are on mute, so if you have a question, want to make a comment, please use your dashboard to mute and unmute yourself. We'd ask that you keep your microphone on mute when you're not asking a question or making a comment. Charles and Mike would like for you to ask questions during the presentation, not necessarily wait at the end of the presentations. You can also submit questions. If you do not have a microphone, you can submit questions on the dashboard, and it will be presented to the participants by the webinar moderator. The webinar is being recorded, so it can be viewed at a later time, and this is a website, and it was included in the email distribution that went out. If you want to go back and look at the webinar, or if you have other people that may be interested in the webinar, we highly encourage you to pass this webinar link to your colleague, so that if they have interest in the subject, they can go back and view the webinar. If you know of other people or organizations that may have interest in research, we certainly ask that you get in touch with Mr. Charles Ellis and Dr. Mike Hamilton and make introductions, make the contacts between the people who have the interest and the researchers. After the webinar, there will be a short survey. We'd ask you to participate in the survey, and so that we can get your feedback and improve these webinars in the future. So at this time, we'll move into the technical content of the webinar. Our two presenters are Charles Ellis and Dr. Mike Hamilton. I think you were all, a bio was emailed out on the two individuals. Charles is a research faculty member in the Electrical and Computer Engineering Department at Auburn. He specializes in micro nanoelectronics and 3D packaging research. He's the director of Auburn's Micro Nanoelectronics Research and 3D Packaging Laboratories. Dr. Mike Hamilton received his BS degree in electrical engineering from Auburn University in 2000 and an MS and PhD degrees in electrical engineering from the University of Michigan in 2000 and 2005. From 2006 through 10, he worked at MIT Lincoln Laboratories in Lexington, Massachusetts, where he worked on a range of advanced electronic, sensor, and integration technologies. In 2010, he joined the Electrical and Computer Engineering Department at Auburn as an assistant professor. He is also the assistant director of the Alabama Micro Nano Science and Technology Center at Auburn, and he's currently leading research efforts in packaging and integration of dense, high-speed, high-power electronic systems. So Charles and Mike, will turn it over to you at this point in time.
Okay, thank you, Rodney. This is Charles Ellis. I'm going to begin the webinar today and talk about the Auburn Microtronics Center here and the fabrication and 3D packaging facilities. And I'll get started. Mike Hamilton will come in after I finish mine and do the second half of the webinar. This is kind of an introduction here to kind of know who's talking to you today. And the major research areas that Auburn, over the years, gone through quite a few different focus areas, but presently some of the major focus areas are looking at 2.5D and 3D packaging and assembly, some MCM development, including depackaging and repackaging and miniaturization. Superconducting ALD films is a very recent addition to our focus areas. MEMS research and development we've been doing for many years, but continue to work in that area, and also failure analysis. I want to kind of, through the webinar here, introduce you to some terms that you may have seen. Many of you may be familiar with these, but just in case you're not, we want to kind of go through some of the terminology that you'll hear, and through the webinar, hopefully understand what some of these items are, the difference in 2.5D and 3D integration, what an interposer is, what through silicon vias or TSVs are, what is a chemical mechanical polishing and how does it differ from grinding, and what is atomic layer deposition. We'll cover a lot of other stuff, but these items are some that you may have seen recently in journals or seen some of your readings, but maybe didn't quite understand. So we'll try to clear those up a little bit more. 2.5D and 3D packaging is an area that Auburn is actively working in, and basically the difference in 2.5D and 3D is that in 2.5D you really don't have die stacked on die, as you see in the bottom part here under 3D. In 2.5D you'll have an interposer that might be on a SIP or system and package chip stack MCM type substrate that has an interposer on the top, and we'll talk a little bit more about what an interposer is on the next couple of slides. But an interposer basically takes you from the fine pitch die solder pads to a pitch that SIP or a SIP substrate can handle, and then typically on the other side of the SIP substrate you have the pitch that a printed circuit board can handle. Again, with 3D packaging, a lot of times you have die that will have through silicon vias, as the interposer has through silicon vias to get you from one side to the other. The die, in the case of 3D, will have through silicon vias in the die, and they'll stack and then stack on top of an interposer, again on top of a system and package substrate. At Auburn we have a lot of assembly equipment. The major pieces I'm showing here is an MCM screen printer, which typically screen prints solder paste, dielectrics, things like that onto substrates. The GSM pick and place machine is one that will automatically, using vision and pattern recognition, can take chips and place them, can take chip capacitors, any kind of small component, and can take them from reels and place them very accurately onto printed circuit boards, or the interposers or MCM or SIP type substrates. And then the Heller reflow oven, the 9-zone furnace that will take and reflow, activate the flux, and then reflow the solder. You can see kind of a typical stack up that that we've done here and are certainly capable of doing is to take a chip with solder balls, place it onto an interposer using a tin lead solder. We have other solders that we're working with now, lead-free solders that we're doing some investigations on. Take the interposer and then connect it to, say, a printed circuit board. Those would be stacked and then placed in the reflow oven and reflowed. And that's what we're talking about. This would be a typical 2.5D packaging assembly. When you talk about interposers, give you a little better idea what an interposer is. Again, typically, many times when they talk about interposers nowadays, they're talking about silicon interposers. An interposer will have thin film normally on top, which will reduce redistribution layers, will take your fine pitch solder balls and redistribute them to the TSVs, and then the through silicon vias are typically holes that are in the silicon that go all the way through and contact the other side. What I'm showing on the top left and right here are some of the upper metal of the thin film that's on the top surface and many times on the back surface of the interposer. And so again, you'll go from these thin film circuit through the silicon to the back side, and on the bottom right we've shown a back side of a substrate where it's just after polishing. Typically during the processing, and you'll do what's called blind fill vias. You'll fill these copper vias or through silicon vias up with, or you fill them with copper, and then at some point when you're through building the thin film on the surface, you'll then come back and grind away the backside until you hit the backs of the TSVs, and that's when you have the full connectivity between front and back. And you can see again on the bottom right here, that would be what a backside would look like right after grinding. Just to give you a little explanation of what a TSV is so that you'll have a good understanding when you see that term of how these things are done. It almost seems like magic sometimes, because what you really want to do is you've got this hole that can be, in our case, a lot of the ones we're recently working in will be 120 microns deep and about 20 micron diameter. And I've got to fill this hole up with copper, but try to leave very, very little copper on the surface of the wafer, because all that copper eventually has to be removed by a CMP process that we'll talk about in a minute. And that is a time-consuming process, and so you typically, for many reasons, want to leave a very, very thin layer of copper on the surface, but you have to completely fill this hole. And the copper plating manufacturers have come up with a technique which uses different additives. The PEG you see here is going to be what's called a suppressor, and that'll be the little squiggly lines you're seeing here. And then the SPS is an accelerator or a brightener. You'll hear it called sometimes, and that'll be the yellow dots. And then we'll talk about a leveler, which is the normal third additive here in just a minute. When you place a wafer that's got a continuous seed layer all the way down in the hole, and you place that in the plating bath, typically the slow diffusing suppressors will attach to the surface, and then the very fast diffusing accelerators will diffuse down to the bottom of the hole. And you'll accelerate the plating with the accelerator, and again, as the name kind of implies, you'll suppress the plating at the surface, and that'll be the first step. As the plating progresses, you've got very fast plating in the bottom of the hole. Your accelerator will tend to concentrate at the bottoms of the hole. It does not get included in the film, so as the film progresses, the accelerator will concentrate at the bottom, and then that will increase, as you see on the right side here, again suppressing the plating at the surface. And as that continues on, you'll finally fill the hole, and if everything's done just right, you will not have any seams or voids in the middle. And then as a final step, you'll add some leveler that will keep that very concentrated accelerator from causing a bump in the surface. And I'll show you in the next slide what a bump looks like. And so that's how they do the TSVs, and this is what there's a lot of research, and we've done a lot of research in this area, and a lot of research actually in the chemical analysis of keeping the additives at the right levels so that you can do this process on a repeatable basis. Some of the Interposer thin film process development, just to give you an idea of how we here at Auburn are doing the different metal layers. We've got different ways of doing it, but this is one of the more recent methods that we have developed to give us the conductors and the vias for this thin film process. It'll begin with a silicon wafer, put a silicon dioxide on, deposit a seed layer, and then pattern where the conductors or the RDL or redistribution layer will go. We'll pattern about a 3 micron copper layer for those conductors, strip the photoresist, leaving the seed layer. We then come back in with a second photoresist layer that defines the vias, and vias again in this case are the ones going between metal layers. The next step is to strip that photoresist and then apply our dielectric. That's going to be the intermetal dielectric between the different metal layers. At that point, we come in with a CMP, or chemical mechanical polishing step, that will polish this dielectric away and planarize the surface. And on the right side, bottom right here, you can see where we've done that for multiple layers. This is a 3-metal layer process. You see the bottom copper layer, you see a dielectric, a middle layer, a second dielectric, and then a top layer, and you see the vias that connect the different layers here. Just to give you an idea from a cross-section and top view of that, the top left photo shows you a cross-section of some of the pillars or the vias with the dielectric spun on, as spun. You'll see they kind of piles up on top of the vias. And the second photo there shows what the top of a via would look like as plated. And it might be 15 microns tall with a 10 micron diameter via. And after some CMP or some of the polishing, we just start to hit on this bottom left photo. As we polish that dielectric away, we're just starting to hit the tops of these vias. And then as you progress with the upper right photo shows a completed one after stripping the seed layer, You can see where the via here is on top of a pad. You can see the center conductor. This would be the via that's going to connect second metal to third metal in the case of building a transmission line. And again, you can see the photo at the bottom right. What's the difference in CMP and grinding? CMP uses a series of soft pads and chucks to allow the wafer and the pads to kind of conform to the surface of a wafer. It can do that over a long range, a large surface area. And grinding typically is very hard, and you'll just flatten the surface basically. So if I've got some raised areas in the case of our vias here that I wanted to flatten, but my wafer is not perfectly optically flat, then I would like for my CMP system to just take the tops of these vias off without, as you see on the right side, what a grinder would do would just grind away all the pads on the right side if the wafer were a little higher in that area, and leave vias or leave some on the left side. And so CMP will give you a very good planarization without trying to flatten your wafer. Now, in case of grinding, a lot of times you want to have a flat wafer, but not in the case of what we're doing. Again, some of the MCM development to show you one that was successfully built here at Auburn, completely fabricated at Auburn University in our facilities. We did a chip for our substrate for NASA a few years back, and it had to withstand about a 300-degree temperature range from -180 to 125 degrees C. And to do that, we started off with a aluminum nitride substrate and did all the plating layers, just a 3-metal copper layer substrate. And then we've got chips that are wire bonded. We've got capacitors and resistors that are soldered on the surface. We've got a crystal up here. And this thing contained a little over 500 wire bonds, and that was all placed in a quite large package. And again, that was all done here. This particular device was using a polyimide material that very nicely matched the aluminum nitride substrate and the silicon pieces so that we could withstand that temperature range. But again, it had greater than 500 wire bonds. We have a polymer wire bonder here, which allows us to do pattern recognition and then get some automated wire bonding. The die harvesting and for reuse is a project we've done many different ones in the past. The right side here shows you a small MCM that the customer was not able to get the die in die form, and so we were given the plastic packages that contain the die. We use some of our equipment here and our expertise at removing the die from the packages, completely removing them from the packages, placing them on an MCM substrate, and then rewire bonding. We have tools to remove wire bonds that will remove all the wire bonds right at the top of the ball, and techniques for, again, getting the plastic removed from the surface and then taking the die out of the package and then being able to reconnect it. A little bit more about our packaging and assembly. We have a full SMT assembly line, surface mount technology assembly line, from stencil printing, fluxjet dispense, robotic pick and place, the 9-zone furnace we talked about, encapsulant and underfill dispensing systems. We can do die attach wire bonding, precision flip chip bonding. We have X-ray systems here to inspect after flipping, to look for alignment, vacuum sealing furnaces for the metal packages and other types of packages where you want to control the environment and then actually do a solder seal or those types of seals, and then some injection molding plastic encapsulation systems. You can see a couple of examples where we've placed die, flip chip die on top of printed circuit boards, directly on printed circuit boards in this case, and then did some underfills. And also an accelerometer, 3-axis accelerometer die on a cube. Some ultra-thin electronics. We have the capabilities for thinning some die and placing thin die on substrates. You see at the bottom here an LCP laminate substrate that we were able to embed thin die within that laminate. destructive failure analysis. Again, I'm going through this quite quick, so y'all, if you have a question, please feel free to chime in here and ask away. Destructive failure analysis and cutting and polishing, cross-sectioning, SEMs, TEM, a lot of the standard things you'd expect to see in from Rutherford backscattering to mass spectroscopy. One of the newer items that we've received recently and have been using quite heavily is our Catan ion milling system. It's got a dual ion beam system on it, so you can take very soft metals, in the case that you're seeing here in the center, some silver filled epoxies and things, where we want to look at how that epoxy has formed. If you try to polish that in most normal ways of physically removing the materials, you'll not be able to see the morphology and just how things have gone, because silver and some of these softer metals tend to smear, and solders and things like that would tend to smear, where with the ion milling system we don't get the smearing. We can really look at intermetallics and a lot of things that are hard to see otherwise. And it's not a TEM. It doesn't take all the preparation that a TEM would require, and it doesn't take the expensive equipment that maybe an ion milling system that you would use for something like this typically. Just to give you a little idea of some of our microfabrication capability and equipment, we have front and backside photolithography, dry etching. We actually have 4 STS systems here on campus now. Wet etching, HF release, we have a critical point dryer, thermal oxidation, diffusion, low pressure chemical vapor deposition, PECVD, ALD systems, which I'll talk a little bit more in a minute. A thin film deposition from sputtering E-beam, we can co-deposit, we can ion assist deposit, a capability of 7 targets, E-beam targets, and 1 sputter target. So really 8 metals without ever having to break vacuum that we can deposit. Plating and dicing, wafer grinding CMP, anodic bonding capabilities, and now can do 4 and 6 inch capabilities in our facilities.
Hey Charles, this is Rodney. Could you comment on the state of art of your equipment compared to the state of the art that other people throughout the nation might use to do this type of work?
I can speak to maybe universities, the types of equipment. I think there are just a few of the universities probably across the country that have the breadth of equipment that we have, and I believe probably one of the only ones that in a single facility would have the assembly equipment that you'll see here at Auburn and that we've been showing, and the wafer fabrication equipment. And so something like an interposer, for instance, we can actually fully fabricate the interposer and also do the assembly all in the same facility, in the same clean room. And so I don't think you'll really see that anywhere else across the nation that has all that in one facility. And as far as state of the art, we try to stay on top of the latest equipment. Again, we'll be talking about the ALD system that we've just received recently, and that is certainly a really new area of interest in looking at superconducting materials, and some of these new materials that are coming out in the superconducting world are done by ALD. And so we feel like we're right on the leading edge of some of these types of devices and structures, and trying to keep the equipment as new as possible and as up to date as possible. Did that answer your question? Okay.
Yes, it does.
Okay. Talk a little bit about our MEMS. The MEMS has been something that many universities are doing now. MEMS, to be honest with you, is kind of an area that doesn't take an exhaustive amount of equipment, and that something that a lot of universities are doing. And Auburn certainly has been doing that for a while very successfully, and have a lot of faculty involved in MEMS processing and development. We have all the CAD tools and design and simulation. We've worked on electrostatic, mechanical, and microfluidic simulation and structures. And I've got a little video here that for some reason is not going to show up now that I'm ready to do it. maybe on the webinar they may not allow it, but we've done some different types of MEM structures here. One that I had a video of here, but for some reason not showing up now, is an inchworm drive where we used electrostatic mechanism to actually move a lens platform around at about 4 millimeters per second speeds. I mentioned earlier the ALD, atomic layer deposition system. Auburn has recently purchased and have in use now a plasma enhanced ALD system, and are building right now a thermal ALD system. And some of the materials you can see up here in the upper right, how uniform these things are. And I don't know if this is going to show up or not. Yep, looks like it. Hopefully you can see this. I'm not sure how well some of these videos do. Are y'all able to see that, Rodney?
Yes, Charles, we can see it.
Yeah.
Okay. It's showing basically what ALD is. ALD is a self-limiting deposition process where you put one atomic layer down at a time, and it's a quite quick evolving technology right now with new metals almost every day, or new materials almost every day that people are putting down. The video here is showing an aluminum oxide process using a TMA, trimethyl alumina precursor that comes in, and those molecules will stick to the silicon or oxide surface, and a second molecule will not stick to the first molecule, and so you only get a single atomic layer. You then put in this case, water vapor that removes the ligands that are on the molecule, and then you repeat the process step by step to get as thick a film as you would like. And again, this little video just shows you a thermal ALD system, again, that Auburn has here also. And we can put down films from titanium nitride, which is a superconducting, and also a barrier layer for TSVs, aluminum oxide, albium nitride, ruthenium, and hafnium oxide, and working on some other films. I want to show you a couple of recent research projects just as an example of types of things that Auburn can do for you and help you, and that we've done for others. One area of research right now is kind of a neat area for a tamper-proof or destruction. We call a destructible chip in a package, a DCHIP, and we've had a lot of technology developed here in the past years from some of our faculty members on miniature fusing systems where they've been able to blow up chips with just a little bit of current, and have some materials here that are a little bit exothermic and able to destroy a chip quite easily with low currents. And so we were going to take something like that and try to put it into a package and package die that have these built-in fusing mechanisms that were just very low charge that maybe could store it on a capacitor at a command could actually go in and completely destroy the chip. And we would package it up into a flip chip type technology, so you'd have these things on the shelf and ready to put into a multi-chip module or however you want to use something like that. But these are the types of ideas and things that we could do with the packaging and assembly and chip fabrication and things that we have here at Auburn. Another one was someone came to us and asked us to build a very thick, high-Q inductor. They had tried many different methods to plate up chemicals. They tried to use photoresist molds, SU8 molds, and different materials, and were unsuccessful, and came to us and asked us how we would do it. We came up with an idea of using our TSV technology and etching a spiral into silicon, and then using the copper filling techniques that we have to fill that spiral, put a dielectric on, put a top metal, and then solder to the chip, and then place the chip on a substrate, and then remove the silicon using xenon difluoride, which is a gas that removes silicon but won't touch anything else. And you can see the chip here, placing it on a substrate, and then after removing the silicon, you can see the spiral here. And this right now is the new state-of-the-art, where what I showed you a second ago at the time was the state-of-the-art, doing 20 micron line of space and about 5 microns thick. We've developed a process for doing 15 micron line of space and could could probably do better than that at 45 microns thick. That's what they had specified for us. But we look at this as a technology that really looking for other applications where we could go from both sides of silicon, do some 3D type fixed structures, surface mount them, and then remove the silicon and come up with sets of antennas, all kinds of ideas for this type of technology, and hopefully we could whet your appetite with some of that. At this point, I'm going to turn it over to Mike. I hope I haven't gone too much into his time here, and we'll certainly have a couple minutes at the end, hopefully, to answer any other questions you might have.
Okay, I'm Mike Hamilton. Thank you guys for setting this up. I know on the title it said nanotechnology, but for the most part I'm going to talk about signal integrity, power integrity, and some of the integration technology that we've been working on, and insert a little bit of nanotechnology towards the end. And please ask questions as we go. So just a little bit of motivation, what's driving this our work in this area, and it's really driven by trying to get to a higher signal density and number, where we're looking at thousands of differential pairs, for example, with very high data rates of greater than 28 gigabits per second, with very low bit error rates. For the power side, we're looking at hundreds of amps to multiple chips and package modules, going through very small areas with very low impedance, less than milliohm impedance. In terms of density, we're looking for extreme areal densities that are much greater than that of the package parts, and also looking at non-conventional form factors for some of these. And then in terms of environment, looking at non-conventional and extreme environments. And this can consist of high temperature environments, low temperature environments, space radiation, as well as one of the most extreme environments, which is the biological environment. So we're driven by these, or motivated by these aspects to create and develop integration technology and characterization techniques to meet the system requirements for these high density, high performance systems. So I've got a little bit of background, and then I'll dig a little bit deeper into some of the techniques that we use. And this is a little bit of an overview here in terms of some of the additional things that that we do that Charles hasn't mentioned previously. So we regularly develop ASIC and RFIC devices. We go through the design, simulation, implementation. We're familiar with using TAPO, so we have access to the processes available through the TAPO and IBM, so the different SIGI processes such as 8HP, 9HP, and as well as the CMOS processes such as 12SO. We also do a lot of PCB design, simulation implementation of those, the multi-chip module development that Charles mentioned previously, and I've got a little bit more details on that. A lot of experience with FPGAs, and then some burgeoning work, I'll say, on nano-enabled sensors and also nanomaterial-based devices and flexible electronics. So we really span a very large space here, all up from the chip and board design, kind of system-level aspect, all the way down to nanomaterials and nano devices. With regards to the high frequency and RF and microwave aspects, we've got access to the necessary design tools such as HFSS and SI-Wave from ANSYS, as well as EMPRO from ADS. Sonnet is another popular one that we use. And so we use these tools to do our design, simulation, and modeling of the systems that we eventually build. And then, as I mentioned previously, we also handle all this interacts with all the SI and PI aspects to develop these high-performance microsystems. So as a quick little example that I'll, again, dig a little bit deeper as we go, looking at the signal integrity as an example for a simulated link performance. There's multiple design flow paths that we take. It depends on exactly what we're starting with and what we're trying to end up with. But for example, here we do our layout in Allegro, so Cadence Allegro, and then extract the nets that we're concerned with from Allegro, import those into ADS, or into ANSYS, run the EM simulations on those links to get typically the S parameters, and then from there we feed that into an ADS simulation along with transceiver models so that we can crank some bits through here and develop eye diagrams. So here we see an eye diagram. And then we can compare the performance of these links to the compliant specifications that are necessary to get these links to be closed. So let's just do, for example, a transceiver setup and see if we can, if the technologies that we're developing will allow us to close these links. In terms of the signal integrity characterization, we deal with a complementary set of frequency domain characterization techniques and time domain characterization techniques. And on the next couple of slides, I'll go into more detail with those. But we also are looking at compliance against standards for these systems, and we can also go in and use some of these same techniques to extract materials electromagnetic parameters. Just as an example, we can use a ring resonator to pull out the complex dielectric constant to give us the permittivity and the loss tangent for these materials, as well as if you use a microstrip material, whatever that system is exposed to, you can characterize it as well. We have a pretty solid set of RF, microwave, and millimeter wave characterization tools. We call that the FASTLab, the Fast Advanced Systems Technology Lab. And in there we have a 4-port PNA that goes to 67 gigahertz. We also have the ability to go up to 110 gigahertz on 2 of those ports. We have a 4-port test set that will allow us to extend up to 8 ports total, so we can do differential measurements, including differential crosstalk measurements. We have a low-frequency network analyzer for doing some of the power integrity. A lot of this work is done on wafer, so we need to probe, and so for that we use a Cascade Microtech Summit probe station. We've got the T-chamber with that. In terms of time domain characterization, we've got an Agilent sampling scope with 18 gigahertz differential TDR, and it also has dual 70 gigahertz remote sampling capabilities, so we can do differential TDR and differential TDT on the integration technologies that we develop. We also have a 33 gigahertz real-time scope, so we can catch glitches to see if we're introducing any issues in these systems. In terms of digital data, we've got a 28 gigabit per second capable BERT from Agilent. We also have a cryo probe station for characterizing at low temperatures. We can get down to 9 Kelvin with that. We also have, I don't mention it on here, but we've got a probe station that's capable of going up to above 300 degrees C. So we can span a very large frequency range and a very large temperature range. And we've also got the anechoic chamber and then a set of power integrity tools that I haven't really covered at all in this, but sources, analyzers, etc. for the power integrity. So here's a quick little view. You can see our network analyzer, our millimeter wave characterization, or millimeter wave controller, and our 4-port extension, the probe station. Back here we've got the TDR scope and the bit error rate system, our probe station. Here's the anechoic chamber. So we have a very comprehensive set of RF, microwave, millimeter wave characterization tools that I'm pretty happy with. So if we dig a little bit down into the frequency domain, a little bit of the educational aspect of this, we typically are interested in bringing out the S parameters. So if we look at a system that would consist of our DUT, that's the device under test, there's an analogy with light in terms of power moving towards, through, and reflected from this device. So we can use S parameters to characterize the amount of power that is reflected and the amount of power that's transmitted through the system, so we can determine how well that system is performing and how it interacts with the rest of the system. We like S parameters because it's a fairly straightforward set of characterization parameters that we can get with a network analyzer. Agilent and related companies have done a lot of work to make a lot of these systems very turnkey, and we can, once we have those data, they're easy to use, and we can relate them to parameters such as gain, loss, reflection coefficient. We can cascade the S parameters, so we can figure out the best way to combine S parameters from different pieces of the system in order to extract the performance of the overall system. And then, since we do use ADS, it's easy to get the S parameters using a touchstone format into our simulation tools to streamline that design flow. Sometimes I get questions about the difference between a network analyzer and a spectrum analyzer, and so here we have a little blurb about what the difference is between those. Essentially, you can think of a network analyzer. It's measuring a known system. It knows what it's sending out of one port and expects to get into another port, and if there's any difference, it's caused by the device that you're testing. The spectrum analyzer is essentially just an analyzer on the end of an antenna. So anything you put into that port, it's going to tell you the power, etc., for the signal as a function of frequency. And then some more details about S parameters in terms of how they relate to the reflected power and the transmitted power. With regards to time domain characterization, we use time domain reflectometry, time domain transmission, as well as eye diagrams and bit error rate measurements. So for time domain reflectometry and transmission, or TDR and TDT as it's often called, we can find impedances and mismatches in impedance, discontinuities, the loss of the structure that we're testing, and use those to do some modeling. And a general TDR system consists of a scope that has a step generator along with a sampler to look at the signal that's going out and coming back in. And in the majority of systems, a sharp edge is used, and due to the Fourier decomposition of that edge, there's a wide spectral content that then propagates through that system. In this being a 50 ohm system, or set up to be referenced to a 50 ohm system, depending on the signal that returns to the scope, we can develop a better understanding of what that system consists of, or what the device under test consists of. So for example, if we know the velocity of propagation, we know the time to some transition, then we can figure out where along that transmission line or cable there's a discontinuity. We can also look at the reflection coefficients to characterize the impedance of the structure that the signal is moving down as well. So there's a couple little examples here. If you send a pulse into an open, then you're going to get this double step configuration as we open that up and see a much higher impedance. Whereas if you send that into a short, your reflected signal is going to cause it to essentially short out. You'll see a very low impedance. So depending on that impedance that is on the end of that the cable or as part of your device under test, you can determine what your based on the signal that comes back, you can determine the impedance loss, etc. for that. So another time domain technique is eye diagram or bit error rate testing. So for that, we're using that to characterize some of the high-speed digital signal transmission structures that we've got. This can become, this is obviously a very light introduction, but this can be a very complicated setup depending on the level of de-emphasis or multiplexing and demultiplexing that you need to take into account based on the systems and frequencies that you're looking at. So a general BERT system is going to consist of a pattern generator and an error detector. That pattern generator sends its bits out of the box and through a channel and then back into the error detector, where that returned signal is compared to the originally generated signal. And in that way, you can do a one-to-one comparison of the data that was supposed to come back and what did come back, and determine what your bit error rates are. So here we see some of the emphasized data that's going out through it. This is actually through a differential channel. And then as we collapse everything back on itself, we can build up this eye diagram that consists of all of the transitions of from 0 to 1 and 1 to 0, etc. And we can also build up bit error rate contours to look and see how wide that eye is and what what the impact of our devices that we're building in terms of integration structures can do to the performance of the system. As an example, this may look familiar. Charles showed this a little bit earlier. This was the thin film redistribution layers that we've worked on for the past couple of years. And this is a differential system, so you'll see the two lines here, and this is it's strip line. Here's another cross section that shows the two signal traces sandwiched in between two ground planes with the nice even symmetric dielectric, which is important to maintain the characteristic impedance of these lines. So we've got the design for this. We run that design through simulation. So in this middle plot, I'm showing the insertion loss and return loss for different lengths of these differential traces. And then the next plot to the right shows them measured. And they're not the same plot. You can look at this first little hump and see that. But you can see we get very good agreement between our measured or our simulated data and our measured data. And this gives us confidence in the models that we use to then go on and determine the impact of these devices on the system performance. We've also got time domain measurements and simulations for this. And in this particular case, we're looking at the impact of inserting a TSV into the signal path. So on the left, this is the eye diagram for that redistribution layer link without TSVs. And on the right, you can see we get some phasing issues, that are leading to a degradation in this eye. So it's still open, probably would still meet system performance specifications, but you can see these. This would allow you to limit the number of transitions that you can, allow you to spec how many transitions you can go through before you degrade your signal. I'll jump from the signal aspect to the power aspect quickly. So I think it's a pretty common knowledge that the power distribution network is going to be a very critical aspect of the systems. It has, if you look at any electronic system, the power side of it is going to be a major contributing factor to the size, the weight, the power, and the efficiency of the system. And we're typically dealing with loads that can draw hundreds of amps, and they switch in the gigahertz range. So in order to handle this and have a nice, efficient power distribution network, we need a low impedance in both the real and reactive aspects so that we can minimize the I2R losses and also minimize the inductive response so that we can optimize the number of decoupling taps that we need. So some of the academic questions that we might ask are how to model a PDN for the fastest simulation. So if you can model the individual components, how can you then reassemble those as models and have a fast simulation so that every time you change something in your power distribution network design, you don't have to go back in and run a complete EM simulation. From the industry side or from our project side, we ask questions such as how much capacitance are we going to need to decouple the inductance that we have for these networks, and where do we put that? So there's obviously parasitic R's and L's for the different components that we have, and these come into play as we go to higher powers and higher frequencies. One region that we're looking at exploring, or that we have been exploring, is in the interposer itself. Form a thin distributed interposer capacitance to place the capacitance in an optimal place directly between where the power is going to be delivered in the chip. So we've modeled a pile of different power distribution network components. Here I've pulled out one where we're looking at some structures in low temperature co-fired ceramic. And the basics of this characterization technique are shown in the bottom left, where we use a low frequency network analyzer in I'll call it a shunt through configuration. So port 1 and port 2 are shorted together, and then the DUT impedance is seen as a parasitic impedance across the 50 ohm impedance of port 2. When you do this, you can pull out the complex impedance of that device structure. And so this is equivalent to a 4-wire DC measurement where you use that to cancel out any contact or wire resistance. So we can do this with low frequency and high frequency signals as well. We'd use a structure like this where up in the top left we have 2 coax connectors, and in the middle we have the structures that we're trying to characterize. In this case, it's a couple of beams. And the takeaway from this chart is we're able to, over a relatively large frequency range, get good agreement between the models that something like HFSS would spit out and the measurements that we make using the system shown here in the top left. And so we can simulate things like 1 via, 3 vias, 15 vias in parallel, etc. Use that to see what we need to do to drive that impedance down to acceptable levels to meet our power distribution network specifications.
Excuse me, Dr. Hamilton. We have a question from Stan Graves, the participant.
Okay.
Go ahead, Stan.
Yes, I guess both either for Dr. Hamilton or Charles Ellis. Back to the early part, there was the mention of using the CMP process for finishing mass-produced or microchips. And Intel and Motorola and others do that extensively in some of the Asian companies. Is there anything out there in the industry that would eliminate the use of CMP in the near future? Are there any new designs? I ask that for a very selfish reason because we're involved with a company that sells a lot of that product into the industry. Is there a new chip I need to be worried about?
Not that I know of. CMP is, even with the newest 10 nanometer, 14 nanometer devices that are coming out in the next few years, CMP is the primary method because once you went to copper conductors, which all modern structures are pretty much using copper now as a conductor on the ICs, once you went to copper, there's no real easy way to dry etch them to get these small dimensions that they're at. And so the only way that I know of in the near future to planarize and to generate these very fine lines in copper is CMP. There's just no other way right now to do it.
We're affiliated with 3M Corporation in their pad dressing devices, and so that's good to know. Thank you.
Yeah.
The only thing I could add to that is that as nanotechnology progresses, techniques such as self-assembly and 3D printing of these structures may eventually come into play.
That could be many years down.
Oh yeah. When it comes to the super high performance, high density, billions of transistors on a chip kind of situation, you've got to planarize. There's no way around it.
Got it. Thank you so much.
Okay, I'll jump back on track here. Okay, so just from this slide, what I was trying to portray was that we've got a design that we use, in this case a fairly complex design. We're looking at 4 chips that are connected all together with all of their transceivers, and they're also pulling a lot of power. So a design like this would drive the signal integrity and power integrity performance that we would need to take into consideration. In terms of the specific integration technologies, or a couple of examples of the integration technologies that we're using, or that we're looking at for dense electronics too, that I've pulled out here, are the building of a liquid metal reworkable interposer. So we have an interposer structure where we make holes. You can imagine that this is a TSV process where instead of using copper, we fill that with eutectic gallium indium, which is liquid metal at room temperature. Now you can see the X-ray here. We get nice, good filling of this. And so this is an active area of our research. We're looking at the DC and RF performance of this. And the idea would be that you could plug and unplug this top chip from a reworkable perspective. In terms of a compliance interconnect structure, we're looking at some double helix contact structures. So these traces down here in the middle image are helix structures of copper that are plated up sequentially. And we can use that as a compliant interconnect structure for things that may have differing CTEs or be seeing large temperature swings. So I mentioned I'd slip a little bit of nano into here. We actually are doing quite a bit of nano materials and devices work here for one reason or another. So just a quick notion of what we mean by nano. So at least one dimension is in the 100 nanometer or below regime. These materials typically exhibit emergent properties that are caused by their size, namely because it's all surface area. There's a ton of surface area in these structures. And there's a large impact on the charge transport through these materials, the optical properties, surface modifications for packaging, etc. So a few examples here. On the left, we've got arrays of CNT bumps that we're looking at for using as packaging, interconnect, possibly sensors. In the middle, we've got some zinc oxide nanorods that are grown from a solution that could be used for gas and optical sensors. And then on the bottom right, we've got interesting technology that we developed that we call black amorphous silicon. So black silicon is available, but that's done with, say, for example, a silicon wafer. Here we deposit an amorphous silicon layer even on top of metal, and then come back and do the etching process to develop this high surface area black amorphous silicon layer that can be used for photovoltaics, packaging, interconnect, etc. In terms of the, Charles mentioned earlier the ALD for the superconductor layers that we're developing. So I've got a little blurb here on the infrastructure development that we're doing for very low temperature systems. By very low temperature, I mean below 4K, so below liquid helium temperatures. And we're interested in looking at the signal integrity aspect of delivering very clean and precise microwave energy to the systems that we're interested in down that need to operate at these temperatures. And these could be very low noise detectors, long wave detectors, etc., quantum devices. And for example, an example of what we're doing right now is this high signal density superconducting flex cable. In terms of flexible electronics, the example that I've pulled out here is using our inkjet printer. We've developed some copper and silver memristor devices. I won't go to all the gory details about memristors, but they're essentially two-terminal memory devices that depend the resistance state switches between a low state and a high state depending on the amount of current that is flowed through that. And it's a reversible process, so we can use a very simple inkjet printing technique to develop a very nice low power memory technology. And right now we're going from, say, the micron scale down to the nano scale for these devices. Okay, so I think we've covered essentially everything on here. This is just covers a couple of our current and recent projects, but due to the time constraints, I think I'll just skip forward a slide or two. And I guess I'll go ahead and summarize this. So essentially, what we wanted to get across was that our team comprises several experts with many years of experience across a range of disciplines that include micro nano fabrication, MEMS, power electronics, packaging, integration technology, a lot of RF and microwave experience, and moving into the nanotechnology world. Hopefully you've seen that we have a fairly complete set of design, simulation, fabrication, and characterization facilities, and I believe that puts us in a good position to support the research and development activities that you guys might have with regards to electronics and integration technology for computing, communication, and defense systems. So in terms of what we offer, a little bit of marketing aspect here, we believe we're working on relevant research areas. Again, a sufficient set of tools to use here. We'd love to work very closely with our sponsors, and we actually have pretty strong SBIR and STTR participation, and we're always looking for other opportunities to push into other areas and to push this further. We believe we've got a cost-effective research option, obviously energetic and experienced faculty, staff, and students, and for some folks it becomes a source of employees. We've placed a lot of our students who work on projects with our sponsors, with those sponsors, and so that's our product, if you will, is the students, since we're at a university. So in terms of contact info, we've got this up here. I'm Mike Hamilton, and there's my contact info. Here's Charles's contact info. And obviously feel free to contact us anytime with questions on this or anything else. And for some people, we're not very far away, so we'd love to have you down for a visit. And I think that does it. Thank you, guys. Thank you.
Rodney, any questions?
Are there any questions? Okay, if there's no questions, Stan, would you like to say a few words this time?
Yeah, I'd like to thank Dr. Hamilton and Charles and Rodney and the staff for doing this. I'd like to say I understood every word, but that would be a massive lie. But I guess I appreciate everybody for doing this. I think one of the things we as a committee need to do, and Rodney help us to determine how effective we're being, other than learning a heck of a lot, is how much feedback are your researchers getting from us, and what else can we do in that arena to help them? And maybe Dr. Hamilton and Charles might tell us some of the companies that they have done sponsored research with, and maybe who are some candidates they would think they might be helpful for. And again, thank everybody for their participation.
Stan, would you like some of that feedback now?
That'd be wonderful.
Okay.
Yes, some of the companies.
Yeah, so we've recently started projects with Intel and Microsoft, so a couple of pretty big hitters, I think, there.
Sure.
We've definitely done work with Harris in the past.
Texas Instruments.
Yeah, Texas Instruments. We've got another project going on right now. It's coming through from AMRDEC through Torch, and that's some of the nonlinear electronics that we're working on. That's actually a very exciting aspect that I didn't talk at all about here.
We've got some DoD projects we've worked on. We can't talk much about those, but do DoD. We've done some DoD projects in the past. We'd love to work more with MISIC and maybe some of the groups up at the Army, or NASA, some of the groups up there, that some of our newer facilities will allow us to do a little more work that may be more applicable or more interesting to them. I won't go into that, but we'd love to talk further with some of those groups.
And I think there's multiple ways, obviously, that we could work. In some instances, like for example, we've worked with Aegis Technologies as almost a service center, if you will. We've got the tools and capabilities here. Some of their employees come down and work with us to make measurements of their devices on our facilities. I know Charles has done fab runs for many of the companies in the Huntsville area. But then that's kind of the service center approach, if you want to call it that. And then there's the funded research projects, where a well-defined, time-limited research project it could be put into place with specific project goals. Another aspect of this too, just to let me run my mouth here for a second if you want, is in the majority of cases, we're mainly looking for funding to support our students. As I said, that's really, that's our product when it comes down to it. So we want to make sure that they have access to the right tools, the funding that they can focus, and the contacts at the companies to interact with. So hopefully that gives some perspective on where we're coming from.
Thank you. Well, again, thank everybody. Rodney, thank you, and Vicki and staff, and look forward to another great program next month.
Okay. Our next webinar will be the 14th of August. We currently have Drew Hamilton scheduled to talk about the Auburn Cyber and Research Center. This presentation has been recorded. You'll get a link to the recording. It'll also be on the OVPR website. So if you have contacts or colleagues that might be interested in this topic, we please ask you to pass it to them. And if you have any feedback, any contacts that may have interest, also to get those to Charles and Mike. Appreciate everybody participating in the webinar. Thank you very much.
Thank you.
Thank you.